So, as it's been said already, the problems associated with increased fuel costs, problems associated with emissions such as NOx, SOx, particulate matter, future legislation to do with CO2 emissions, and setting up of ECAs and SECAs, and even more stringent regional port emission limits, for example, west coast of the US. These are all issues that are being dealt with by IMO and EU exhaust gas emission legislation, and TEFLES Project was set up to look at and investigate issues around that. So in detail, the project was to look at 3 technologies and strategies associated with after treatment and thermal energy, looking at exhaust gas cleanup, exhaust gas energy recovery, and thermal energy in port. Also in propulsion and manoeuvring, looking at hydrodynamic technologies, and in power generation and propulsion, ship performance, modelling, alternative propulsion, utility drives as examples. Those are the 3 strands in terms of the technologies and the strategy, but also looking at 3 scenarios. The scenarios are at sea, manoeuvring in port, and alongside of port, and looking at the technologies and the emissions associated with those scenarios. It reduces obviously the emissions while in port, so it's an attractive option from that perspective. It requires connection technology on board the vessel itself. It also requires large port infrastructure investment in terms of substation connection to the grid and shore-based ship connection points. Integrated refrigeration and thermal storage in port. At sea, we've been modelling recovering of the exhaust gas heat to drive absorption refrigeration system so that it can provide the cooling requirements, but also putting in parallel with that an ice slurry storage system so that the storage could be utilised in port and when exhaust gases are no longer available. The study has looked at the size and is determined by the length of stay, obviously, of the vessel and its requirements for cooling. And for the Rolo vessel that was looked at in the case study, it required about 160 kilowatts of cooling requirement over a 15-hour maximum stay in the port, and that was sized to require a cooling storage system about 25 meters cubed. And obviously this depends on the type of load for the type of vessel, the air conditioning, chilled water, and the refrigeration requirements. Distributed CHP generation using alternative fuels. Primarily, studies have looked at the generation of power and, for example, using LNG in a cogeneration plant. The provision of power is one thing, but if you're basically shutting down a vessel in port, the vast majority require some form of heating. That can either be introduced on board the vessel or actually has to be supplied from shoreside. And those options are possible from a land-based CHP system. Otherwise, a large amount of energy is wasted in low-grade heat. So this has the potential to reduce emissions significantly, just as LNG does if used on the vessel. So a reduction in CO2 emissions at 24%, NOx by about 80%, sulfur emissions minimal, and particulate matter also. Potential for reduced fuel costs, because lower, as we've just heard, in terms of MDO and HFO. It's costly infrastructure. The other technology that we have been looking at is to use secondary methods of emission abatement, and that's to use exhaust gas cleaning system. This is based on technology developed by a couple of systems. It's a dry exhaust absorption for auxiliary engines. It's a two-stage system. It removes particulate matter, NOx and SOx. And the reduction estimates are around 80% in particulate matter, 95% of NOx, and 85% of sulfur emissions.
I think I'll just start off with one question: why bother? A lot of studies have been described saying the increase in asthma in children and all the related medical problems, but I think it can be simply summed up in one word as focus. And that now there is much increased focus on all these issues, which maybe perhaps in the past were not as up on the forefront. Whereas now a ship being in harbour is close to habitation, is a very direct impact, and it's also very immediately apparent. And hence, the addressing of emissions while in port has an immediate impact on the focus on emissions. So first off, we'll look at the electric option, which is the cold ironing. The idea is that the ship is berthed and is simply plugged into the shoreside grid. Will it give benefits? Will it give actually increased emissions? As part of the project, some feedback on cold ironing was obtained from a number of different ports, showing what ports think is the benefits of cold ironing, what motivates them to go for cold ironing, and what keeps them back from actually implementing cold ironing. Starting from the negative aspect, the cost of cold ironing and the economic side of it is clearly the biggest drawback. Cost is associated with all the devices on board, as well as the infrastructure on shore. On the positive side, environmental benefits, as well as compliance with regulations, is clearly the big motivator to go for cold ironing. And when the cost of shoreside energy generation in terms of normalized cost per kVA is much cheaper than cold ironing, the solutions show there is a cleaner benefit in terms of going for shoreside LNG. The reason being that for a cheaper cost, you can get a relatively good emission saving as well. Now, this particular slide shows only the CO2 emissions. In case of the SO2, clearly it would be a big benefit in all particular cost values associated with shoreside LNG. When the specific cost of shoreside LNG increases to be on par with that of cold ironing, the advantages of going towards shoreside LNG are not that clear. Clearly because you will not be getting as much emission reduction for practically the same cost. Now, as a cost value, we've assigned the per unit cost of shoreside energy generator to be relative to that for a frequency converter, to give us a relative comparison. I think that sums up some of the work we've been doing on comparing cold ironing on shore. It has clear environmental credentials, but its feasibility is not universal or automatic. A feasibility study must be performed for each particular case, depending on the frequency of ship visits, how long the ship is in port, and all the associated factors. The emission savings are highly dependent on where the ship is being berthed. In some cases, we'll have very good improvements. In some cases, the savings are not that clear. With current generation mixed values, also, the SOX improvements are not that clear. And finally, it also provides a good comparison to shoreside LNG generation, and that the variability of costs will sometimes make shoreside generation be much more cost-effective compared to connecting to shore with all the associated electrical infrastructure.
Aquí voy a hacer una presentación centrándonos dentro de los escenarios que mencionaba Tony en la presentación inicial del proyecto, cuando nos vamos a centrar en los dos tipos de buques que hablamos, que es el buque Rolo y el buque remolcador de puerto, y viendo la operativa con las estrategias de propulsión híbrida analizadas durante el proyecto en las maniobras de puerto. En lo que es la tecnología de propulsión híbrida que hemos analizado en el proyecto, haremos un análisis de las particularidades de cada tipo de buque, de las opciones de propulsión híbrida que se analizaron desde el punto de vista de retrofitting y nuevo proyecto, y luego el análisis de la maniobra de los buques, tanto del Rolo como del remolcador, en las maniobras reales que se basan en datos de mediciones realizadas a bordo, en la ruta de Vigo a Saint-Nazaire y en la salida del remolcador de puerto desde Vigo a buscar el buque en la ría. Y luego las conclusiones y la presentación del modelo numérico empleado. Nosotros creemos, dentro del proyecto, en el análisis inicial se determinó que las opciones de propulsión híbrida eran las más óptimas para la integración de la tecnología eléctrica en la disminución de emisiones de este tipo de buques, los rolos y los remolcadores que les dan apoyo en la maniobra de puerto. Y es debido a que en el mundo ideal posiblemente haya el día de mañana unas fuentes de energía eléctrica de alta capacidad y muy compactas y muy baratas que permitan que los buques sean eléctricos como lo son los coches, pero aquí el planteamiento en un buque es diferente por la cantidad de energía que está involucrada en su operación. Y entonces nos centraremos en las alternativas de propulsión híbrida, en las aproximaciones a puerto, en las que la demanda de potencia es muy reducida y es posible hacer una reducción de emisiones en ese área, que es la que nos interesa por estar cerca de las zonas habitadas. Y estas propulsiones híbridas se van a basar en la combinación con los varios subsistemas existentes. La planta propulsora es muy elevada. Para poder hacer un accionamiento auxiliar eléctrico necesitamos cambiar a mando combinado, no se puede hacer RPMs constantes, o bueno, no es económico hacerlo, por lo que os comentaba del rendimiento. Accionar una propulsión RPMs constantes desperdicia mucha potencia. Entonces, bajando las vueltas, hacemos que fijaros aquí, la potencia con el buque parado está consumiendo 2190 kilovatios, esa hélice batiendo el agua ahí en la popa. Cuando si trabajando en mando combinado son solo 750. Y a medida que vamos aumentando velocidad del barco, vemos que con el mando combinado somos, con un motor de 1 megavatio somos capaces de propulsar al buque a 7 nudos, mientras que a RPMs constantes necesitamos 2,7 veces más potencia. Usando los grupos, porque hay un ahorro, porque por un lado tenemos esta reducción de potencia y hacemos también que los grupos trabajen con más carga, que es algo habitual, que los grupos dieselgeneradores están trabajando con cargas muy bajas y al nosotros transferirle la carga de la planta eléctrica adicional hacemos que se metan en puntos de consumo específico mejores, que puede ser por ejemplo el 90%, mientras que el motor principal en estos puntos está trabajando en un punto sabíamos que eran 15 megavatios, pues en un 30%, ¿no? Un 30 no menos, será un 15% de la potencia. Bien, en el caso de que se usaran un complemento de baterías, el cargo sería lo ideal que estas se carguen en puerto, porque la carga de las baterías en la mar apenas tiene efecto en los ahorros. Bien, aquí tenemos las cifras. Realmente lo que interesa es la comparativa de la situación actual con la propuesta con el accionamiento eléctrico. cada una de estas máquinas son las tres configuraciones que vimos antes, que prácticamente arrojan los mismos resultados, pero sí que hay una reducción de las cantidades de combustible consumidas en esta operativa. Y para el remolcador, con las diferencias son prácticamente nulas, porque todo el mundo se esperaba que para el remolcador se obtuvieran unas mejoras mucho mayores. De hecho, es uno del tipo de buque en el que se están haciendo mayores inversiones para el cambio a propulsiones eléctricas, pero no hay una gran mejora en el consumo específico entre los grupos y el motor principal. El motor principal de los remolcadores ya trabaja a velocidad variable, es un motor que está mucho más adaptado a ese servicio y no se producen grandes ahorros. Aquí la clave, ¿dónde está? La clave está en el perfil de operación de ese barco. Sí, esto es el buque en el puerto de Vigo, atendiendo a este tipo de tráficos, pero los remolcadores pueden operar de muchas maneras diferentes y lo importante es que cada armador, a la hora de hacer una inversión o plantearse un retrofitting, que conozca muy bien el perfil de operación y tenga datos reales de dónde lo va a aplicar. O sea, no hay una solución mágica de...
I think that when we are trying to analyze these possibilities, I would try to make a reflection on where and how to do it. I mean, in order to succeed, we try to choose the better places and try to make the audiences. I mean, if we try to make very general conclusions where you say at any time LNG is a good question, we have a negative conclusion per se. If we begin to think on coal ironing, then we say we can have coal ironing for Rolo vessels, we can use batteries, and I would try to be pragmatic. I would try to think which pragmatic way we can use all reactors, ship owners, port authorities, stevedores, in order not to begin to build something that in the end is not economically sustainable. So I think we've taken an example in Vigo, a particular example which can show that some things can be done. So with thinking in other cases we've had in the past in Europe, to try to be very realistic on that. To be realistic doesn't mean that we don't have to do it, but to be realistic means that we should choose the better place to develop this. And the other thing I wanted to add also is that when we talk on emissions, we don't have all I think that the analysis should be done not only with vessels, but we do all around the inland side of the port. So we try, when we work with port operations, and we think on trucks, on cranes, on forklifts, and we also try to make us, with the ship and stevedore companies, we organize in a good way the operations. We can get quite a big amount of emission reduction. When we are working with the Spanish port authorities, and when we were said before with the President of the Portuguese States in Spain, that we have in Spain a special agreement where you can get a benefit. And we've been working with very simple things that work. I mean, we talk about how to put the trucks, how to organize the operations, that you have lesser emission because you use lesser trucks. We work with the crane companies, modernizing the way the cranes work in order to use the whole strength of the crane itself. So with that, we've been able also to reduce emission inland.
Kind of immediate, pragmatic, as opposed to research. I took part in a research project with Marine Tech in Norway 20 years ago on LNG combustion, and it's only now really being picked up in a big way. So research is one thing. We have to kind of think a little bit further ahead very often, and time catches up with us.